Let's go ahead and pray for our day and our week and our second half of the semester. That was amazing. You can always tell who the kids were who were the problems in elementary school.
I was homeschooled.
Okay, so you're definitely a problem.
Problem with the house.
In the house, wrecking things. It's all right. So we'll pray for our second half of the semester. How did the weekend go? You got to sleep? You got to sleep? Is that the big thing that happened over the weekend? There was sleep. That's good. Yeah. I didn't sleep, and then I almost died, and then I woke up. I was driving down to, literally, I was driving on 77 in West Virginia, and I'm like so tired. This is like I don't know, it's in the morning on Saturday. And all of a sudden, I feel the car jerking, and I'm like, oh, I'm in the median, and I see a sign coming towards me, and I was like, swerve, and my wife woke up, and she says, is everything okay? I was like, I just hit the rumble strip. and she's like, I think I need to take over for you. And so she took over, and I slept. So that was it was a little bit of a scare there, but we did here. I will show off though. I don't know. Have I showed off? Yeah, there's the baby. That's why we were almost died. So here he is. Isn't he happy? He's so happy. So there's my wife with him. There he is doing something. I don't know what's going on there. Yeah, it's this little guy. I know. Yeah, you can tell any unusual photo is one that I took. Sorry to impose this on you. Oh, there. Okay, this one you should like. Got the MVNU onesie. So, yeah, he's there. His expressions are great. He's like, what the heck are you doing to me? Oftentimes he'll just be like, I don't understand, but I guess I'm going with it.
I love the picture of you too.
Oh, you mean this one in the car? This is on the way to church. Yeah, see this? That one? Selfie. I was in the back seat with him.
It's perfect.
Yeah. Well, I thought so. I thought so as well. But okay, so let's see. How do I get rid of that guy? Okay. Well, anyway, so we can be. So I guess I am thankful. I'm thankful that I'm alive, because I was literally in the median, and I didn't lie to my wife. I was like, yeah, I was off the road there. So I oftentimes exaggerate for comic effect in stories I tell, but you're probably used to that already, or maybe you don't know. Maybe you thought that everything I told you was the truth. Okay, hopefully that's not the case. But anyway, well, let's pray for our second semester. Lord, thank you for this weekend. Thank you that we could sleep when we needed to. Thank you that I didn't die. Thank you that that I could go and see my grandson. And I thank you for this group and this second half of the semester. I pray your blessing upon these students during this next 6.5 weeks. May they see your truth and enjoy the time that they have to learn and grow and develop into the people you want them to be. Guide us through our lesson today. Help us to see your truth in the language of mathematics. I pray this in your name. Amen. All right. So why are we here? You have a test. So this test, here it is. Where is it? Yeah, I showed it to my son-in-law. My son-in-law was a computer science major. He's making more than twice what I make here as a computer nerd. But anyway, he had taken discrete math, and he's like, oh, let me see that test, because I was grading, or no, I was grading my calculus test, but I happen to have this sitting on the table. And so I gave him the blank one, and he's like, well, I kind of recognize some of this stuff, but I couldn't do it. And then he's like, oh, combinatorics. And it's like, oh, I can do problem 5. So he did problem 5. He was very excited. But anyway, if you could not do problem 5, please do try to learn problem 5. Also, I need to apologize about problem 4. A number of you were tried that multiple times and wasted time. I apologize. I tried, when I'm making these up, I think, okay, I can make this collapse down into just two nodes. And I'll tell you where my mistake was. My mistake, I'll tell you right now, was state 5. So state 5, the arrow that goes up to state 0, do you see it there? That one should have been pointing to state 1. Now, if that had happened, this would have collapsed down into two nodes. There would have been two equivalencies done. But as it was, every node was separate when you got done with the 4 or 5 equivalencies. So you did a great job with that. I feel like you should get bonus points for writing out all those equivalencies. But I wasn't that kind, apparently. What else do we need to look at, though? Are there other questions, concerns? I know that the combinatorics got really hard at times, although I kind of felt like it wasn't as hard as the practice test. But there was still some confusion on some of these. Yeah, the back page should have been very easy. Here's my answer key for the back page. I mean, that's how easy it was. So if you made it, if there was no inclusion exclusion on the back page, that maybe that was what confused you. Is you're like, this should be harder, so you made it out to be harder if you got back page wrong. So anyway, if you do have further questions or complaints, or if you're mining for points, I'm happy to hear your arguments. And in fact, you know what? That reminds me. I think the last exam, Roston, our buddy, some of you know, he mined for points, and I agreed with him, and I never gave him his points, and I still have his exam somewhere from test 1, calculus. So I will eventually give him his points, and I will give you yours if you deserve them. All right, so we're all happy as we can be. Okay. All right, so what are we doing today? We're doing something fun. Well, eventually. So eventually, you're going to get to play with toys, but for now, we need to talk about this. Where is it? Come on, buddy. Work for me. Why is it not working? I'm clicking. There it is. So you have some toys. We're going to use those toys to talk about recurrences. You know what recurrences is? Recurrence relations. Some of you are computer geeks and you know about programming recursive functions or recursive modules or whatever. That's basically what we're doing here, except we're doing it with toys. We're doing it with math. And we're going to solve recurrence relations. So what does it mean to solve a recurrence relation? Well, let's start out with some sequences. Can you guess the next number in each sequence, except for that last one? The last one, I'll talk about that one in a bit, but let's go ahead. These 4, pretty easy. I'll bet you can do this. Take a minute, guess the next number in the sequence. See if you can do it. And meanwhile, I don't know what I need to do. I need to find my randomizer. Oh, look, it came up as a suggestion. Let's find my randomizer. Well, I also need to drop the hammer on these 2 who aren't here. Oh, I should put this on my iPad. It'll be easier to deal with. Welcome, Sam. Did you take the test?
Yes.
You did? I guess I need to track down your copy of the test.
Should be at the testing.
It probably is. I don't know why they didn't send it to me.
I mean, I can retake it.
No. Oh, you think you do better the second time? I've got a blank. No. Let's just go.
I mean, that probably wouldn't be fair.
Yeah, you're right. No, I appreciate your wanting to make everyone else feel good. Okay, so all we're doing is we're solving recurrences. You're guessing the next number in the sequence. We're happy today because we're dealing with recurrences like recursive functions, recursive formulas. It's going to be beautiful. Why is this not? That's what I want. Okay, sorry. I'll get this fixed in a sec. I just wanted it on the iPad so I could write on it. There we go. Whoops, this is, do I need to just throw these away? Maybe. Okay. All right, let's go for it. Peyton, the first one, do you know what the next number is? I don't know. What? Yeah, okay. Peyton, do you know what the next number in the second one is? 83. Where'd you get 83? Wait, which, okay.
Well, I did times 3 and then minus 4.
Oh, okay. Interesting. Times 3 minus 4. Times 3 minus 4. Times 3. This is beautiful. Minus 4 times 3. I love it. That's beautiful. Did you have a different number?
I guess if it's 87, the next one would be 83.
Oh, I'm sorry. Yeah, 87. Did I mishear you? I think I misheard you.
No, you heard me right.
No. I'm confident that it's my fault. Okay, it often is. Did anyone get a different number? That works? This works? Yes? You got a different number? You made a number up? Okay, that's great. Okay, good job, Peyton. That's beautiful. Lucas, I guess we're just picking. Pick a sequence. Tell me the next number.
The first one. It would be 480 times 6.
Ooh.
And that could be, I think, 2,880. Yeah. Only second here. Oh.
Wait, 2880?
Yes. Yes.
Yeah, that's twice 1,440, which is 12 squared times 10. That's so interesting. Okay, so this is times 2, then times 3, then times 4, then times 5. Oh, I see what this is. These numbers, oh, there's a formula for these numbers. This is just 4 times n factorial, isn't it? That's so cool. Then I've got a formula that you figured out a pattern, and I've got a formula for it. I wonder if there's a formula for this. I don't want to think about it. Let's do these other two first. What about John? John, do you want to do one of these others?
I can do the third one.
Okay, what do you got? Wow, how did you figure that one out?
So the first time we had 2, and then we had 4, and then we had 8, so we're adding 2.
Okay, so this is going to be plus 64.
Yeah. Or you could say we have a power that's minus 1.
That's, yes, I love it. Okay, just a minute. Okay. Yeah, I think I've gone too fast now. Let me do this. This is going to be A sub n times n. So you're always multiplying by or times n plus 1. Is that it? Because you take the 4, multiply it by 2 to get the 8. Then you take the 8, multiply it by the 3 to get the 24. And then, so each time you're multiplying it by the position, you're in the third position. So you multiply by 4 to get the next number. Does that work for everyone? Notationally? And then let's use John's description, the initial, not the formula, but the initial description. I'll use C here. So C sub n times 2 to the n. Isn't that right? It's just 2 to the n? Because you take 1 times 2 to the first, 3 times 2 to the second, 7 times 2 to the third, etc., etc. Okay, so by the way, what I've got here is I have 2 different ways to describe these sequences. This is called an explicit description, a formula. It's a formula, so you can say, here's what the value is going to be. You could plug in 1,000. You can tell me what the 1,000th number in the sequence is just by plugging it in here. Same thing goes here. The other one is called a recursive formula. And the recursive formula is useful when you're talking about something local. You're saying, what's going to happen tomorrow if this is the way it is today? So we have this thing, that thing. Hopefully this isn't throwing you this notation. This is the C sequence. The N just refers to the position. It's like a road name, house number, telling you where you are, and this is who lives in that house, are these numbers. Okay, let's do the last one. I'm sure we got this. Gina, what's the next number in the fourth sequence? 75? How did you get that? So I'm going to call this the D sequence. So you do D sub n minus 5. Now, we can come up with a formula for this, can't we? What do we start with? 100 minus 5 times n minus 1, like the number of steps you've taken minus 1. Isn't that the way it works? Let's see, 100. So the second number is 5 times 1. The third number is 100 times 5, 5 times 2, 5 times 3, 5 times 4, 5 times 5. All right, very nice. I love it. We have explicit, we have a recursive formula. Hopefully this isn't too advanced or too difficult. Have you done recursions before? Well, even if you haven't, hopefully you catch on quickly. This last one, there's a story behind it. I was teaching in Philadelphia. This is in 1995, long time ago. Over the summer, this girl comes up to me after class. I was doing something like this. And she says, oh, I've got a sequence for you. She shows me this sequence. And she says, what's that number? Or no. Sorry, she didn't say that. She said, what goes there? So this is the inner city, Philadelphia. What goes there? And I was like, I don't know. So I came back the next day and I was like, 66. No. I said 65. No, I guessed all summer long. Into the summer, I said, you got to tell me what goes there. She said, nope, you can figure it out yourself. So, really? Well, she's right. I finally did, but it took me moving across the city to figure it out. So I was living at the time in an area of the city called Andorra, which is the far northwest corner of Philadelphia. And then I moved to the City Line Ave area, which is, okay, so this is near Fresh Prince of Bel-Air. Over here, no Fresh Prince? No one knows it. I know, this is from the 90s. I thought it might have made a resurgence. Will Smith? Okay, at the beginning he says, West Philadelphia, born and bred, or whatever. Anyway, I was far west Philly, Overbrook area, and I started riding public transit. And what I would do is I'd hop on a bus to get to 69th Street Station, and I would take 69th Street, I'd take the blue line to City Hall, and then I'd take the orange line north to Temple University. I was sitting there on the subway one day just staring, because I don't have a phone, because this is before phones, staring up at the advertisements and at the map of the subway system, and I saw that sequence of numbers staring at me, and I realized, oh, yeah, I would eventually figure it out. These are the subway stops on the blue line, starting at City Hall. It's starting at the river. So Delaware River. So 2, 5, these are the numbers. It goes 2nd Street, 5th, 8th, 11th, 13th, 15th, 30th Street. Yeah, you might wonder, well, what's going on there? There's a Schuylkill River, so the subway goes under the Schuylkill. And then, so there's a huge gap. 34, this is University of Pennsylvania, by the way. 34, 40, 46, 52, 60, 63, 69 was the end. The thing in the gap is Milburn Station. So Milburn goes there. So it's like, oh yeah. Anyway, so that's a long story to get on to the next thing. Let's see, do we want to talk about this? Sure, let's talk about inductive reasoning. So what are the next 3 numbers in this sequence? So you know, you can tell me, right? Pearson, what's the next 3 numbers?
11, 13, 50.
That's 50? 15. It could be 50 though, but it is, the ones I was thinking of is 11, 13, and 15. Now, you could also tell me what the rule is. So Sam, what's the rule? What's the rule that Pearson used? Yeah, you add 2 each time. There's other ways to talk about this rule. You could say the rule is it's all the odd numbers. You could say the rule is you take 2 times a number minus 1, 2 times n plus 1, whatever it is. Anyway, yeah, what's the rule? Yeah, sure. It's we're going to do handshakes now? I forgot about this little thing. Should we do the handshake problem? I think we should. Okay. You know, this took a hiatus during the pandemic. But first day of class in math systems, I used to go around and introduce myself to everyone and say, hi, John Noonan. Gina? Pearson? John Noonan, yes. Okay. Oh, by the way, Sarah, this is Pearson. Now, at the beginning of the semester, people wouldn't know each other. Say, oh, okay, and Pearson, this is Gina. Gina, this is Sarah.
Oh, that's Sarah.
Now, the question is, how many handshakes did we just have? You did one more? That's okay. So And then the question that I would pose to the class is, how many handshakes would you have if everyone in the class shook hands with everyone else? Now, you can answer that question with combinatorics pretty easily, but there's two ways to answer it. There's the inductive or recursive way, and then there's the formula. So if we have everyone in this room shake hands with everyone else, now I'll tell you right now how many handshakes occurred. There were 6. Is that right? Hold on a second. Yeah, there were 6. So let's count the people though. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 of us in the room. What if everyone shook hands with everyone else? How many handshakes would there be? So any guesses? There's, like I said, 2 ways of doing it. You got it? 28? How do you get 28?
Wait, no, I did that wrong. It's not 28.
Yeah.
It would be
I know.
36.
How do you get 36?
So there's 9 of us, correct?
Yep.
So there's 9 people. Each of them are going to shake 8 people's hands.
Mm-hmm.
So you have 9 times 8, but then we're double counting.
Amazing. That is beautiful description of the answer to this problem. Did everyone catch that? That's what I do with the math systems kids, is I describe it exactly in that way. However, you have another tool in your toolbox that the math systems people don't have. That's perfect, by the way. Perfect description. But does anyone know the formula? There's a super quick way of saying it. So if you think of each handshake,
Is it just 9 choose 2?
it is just 9 choose 2. No, but I love your description because, like I said, I do this every time I teach math systems. We go over this, and I'm like, yeah, look, we're all sort of, what is it called? Egocentric. And so I think that when I shook hands with Gina, that was my handshake. Gina, though, she thought it was her handshake. So when I went around and shook 8 hands, those were all my 8 handshakes. Gina did the same thing, but we overcounted. So it's perfect. I love it. So anyway, yeah, that's perfect. Okay, let me write this down. So the handshake formula is n minus 1 choose 2. N minus 1 choose 2 is the handshake formula for n people. So that's a formula, but let's think about this recursively because that's what this is all about. This is solving recurrences, so we're going to have to think recursively about this. We have 9 people in the room. There are 36 handshakes. So let's do this. The handshakes for 9 people are 36. Can you tell me what the handshakes for 10 people are without using the formula? Rather, thinking through what's going to happen when Joseph eventually comes into the room, which I'm sure he will any minute now. And he starts shaking hands, congratulating him that he's here. So how many handshakes will he do when he shows up? What?
This one should be 36. I was right the first time. Because I did the n minus 1 the first time.
Oh. 9 times 8 over 2.
Yeah. So
there's 9 people. Oh.
Yeah.
Oh, no. No, you're right. My formula's messed up.
Wait, really?
Shouldn't it be n choose 2? Okay, now we got to think, I thought it would take longer and we had gone through it. Okay, there are 9 people here. Each of us shake hands 8 times, right? Because we don't shake hands with ourselves, so it's 9 times 8 divided by 2, which is 9 choose 2. So, yeah, okay. So it's 9 times 8 over 2. We're right. You're right. No, it was just me writing it down was wrong. I misremembered. Okay. So can we get from 9 people handshaking to 10 when Joseph shows up? What's going to happen? Who's he going to shake hands with? Okay, well, let's just add, so that's where my n minus 1 in my head is. But yeah, just add 9 because Joseph's going to come in here and he's going to say, and immediately, if he shows up, you got to just shake hands with him, Joshua, or I could if you don't want to. So shake hands, everyone, I shake hands, Joshua does, Peyton does, Sam, everyone shakes hands with him. That's 9 of us shake hands with Joseph. And that means that we're just going to add another 9 handshakes to the count. Whoops, why is this? That's on eraser mode. Hold on a sec. So to get from here to here, we're going to add 9, and we're going to get 45. 45 handshakes. So what's the handshake formula recursively? What if we go from H10 to H11? How many new handshakes do we need to add in if we get an 11th person after Joseph shows up? Another 10, yeah. Because it's the 10 people who are already here. Shake hands with the newbie. That's 55, and so on. So this is plus 10. So here's the handshake formula. Recursively, the number of handshakes will be the old number of handshakes plus n minus 1. Yeah, that's right. So here's the way to think of this formula. Is if I want to know how many handshakes there are with 11 people, I go back to the number with 10 people and add 10 to that. And I get the number with 11 people. Isn't that beautiful? So recursive formula. Now, why am I looking at this and not looking at fun toys? We're getting the toys here. Okay, do we want to do those? No, we don't. Let's do this. Oh, no. Let's do this. No, we'll do this one first. Okay, I want to know the next three numbers for this pattern. Start with 1, 2, 4. You tell me what you think comes next. And I've got a choice. 5 choices. So take a minute, pick the one you like the best, and we will take a vote. Ooh, I should get this set up. Just a minute. You think about it. Pick your favorite. Okay. Whoa, wrong. Sorry. I need to open up a web thing here. Okay, hold on. Okay. All right, I am ready. Let me put this back up here, and then we get back to the thing that we were looking at. There we go. Okay, let's take a vote. How many of you like A? No one likes A? Now, oftentimes when I'm dealing with, or when I'm working with my, dealing with math system students, there will be a few who like A. And they have their reasons. We can talk about that in a minute. What about B? You like B? Oh, several of you. Okay, the computer science. Oh, actually, yeah. Very nice. B. What about C? No one likes C? Wow, that's like this. Well, actually, it's B and C are usually the most popular two answers that people like. All right, what about D? E?
I like E as well.
You like E as well? Okay. Wait, you guys in the middle here, you don't like any of them.
I like C.
You like C now? You don't like any of them?
I like C, but it could be a lot of them.
Yeah. So the answer is that with no other information about this pattern, I've given you 3 numbers. Every single one of them has a reason why it could be that pattern. And I can show you here in just a minute. But for example, B is the easy one to explain. You just say you double the number each time. So it's powers of 2. So 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32. Then the C there is also one that makes sense because you'll notice that we're adding 1. 1 plus 1 is 2. Then you add 2. 2 plus 2 is 4. Then you're going to add 3. 4 plus 3 is 7. And then you add 4. And then you add 5. That makes sense. Okay, what was the deal with A? And what's the deal with D? Now, who liked D? Did anyone like D? All right, I can look these up, though. I have a cheater way of doing this. Here, I'll show you. It's the online encyclopedia of integer sequences. You can type anything in here. For example, 1, 2, 4. And it will list off all the different sequences. So powers of 2 are the most popular. It's like a search engine for sequences. And this has been around since the early 90s because I used this all the time when I was doing my research. Seriously, because it has nice like references to different papers and stuff. Okay, blah, blah, blah. This is such a long entry. But I just want to show you that that's not the only one. Come on, there it is. Okay, so there's this. What in the world is this? Look, it's like, here it is, 1, 2, 4. It's in there. And what is this? It's a table where the nth row is the factorization of n with each prime p replaced by I. My goodness, that's so weird. Why is that the second most popular? Okay, coefficients of this. So there's, oh, interesting. You get all the, seriously? Are those all powers of 2? That's really interesting. Anyway, so let's go back to the top, get back to the top here, and we'll type in each one of these and we'll get the formula because I know you want to know. 1, 2, 4, we've already gotten the second one, which was 8, 16, and 32, powers of 2. Let's do the 9, 20, and 48 because I forget what it was that was special about this, but this is a common, here it is, oh wait, number of unlabeled rooted trees within nodes. I don't think so. Well, I'm just saying that my math systems, my beginning students usually will have stuff like, wow, so many references. Okay, there's formulas. Just a minute. Just trying to see if this one would, why someone might choose this. Okay, no, that's too complicated. That's probably not what my beginning students were thinking of. Is it this one? Number of distinct values taken by 4 to the 4 to the 4 or whatever. I don't think so. Let's see. It's got to be something simple. No. No. Wow. These are weird. These are really esoteric. Yeah, I don't know why. There's some formula. Okay. Well, anyway, you can see that there are a bunch of them. There's pages and pages. Look at this, 5 pages of things. So I'm not going to belabor this because we want to get on to the fun toys. So let's go on to the toys. Okay. Oh, okay. So the first lesson that we learned from this is that without a formula, a sequence, you get a bunch of numbers, you have no idea. In fact, this could be 1, 2, 4, 5, 4, 2, 1 or something. I'm sure I could come up with a reason or a formula that would justify that. So without a formula, we got nothing. So the 2 formulas we're going to be working with are recursive and explicit. And what we're going to be studying is moving between the 2. So if you have a recursive formula, can you come up with the explicit formula? So this is the recursive formula for the Fibonacci sequence. Let me just explain it quickly. I know this is not as familiar to you maybe as what you're used to. I'll write it the way that you're used to this. The Fibonacci numbers, each number is equal to the sum of the previous 2 numbers. So if you've never, and it starts here. So it starts with the first 2 numbers are 1. So you have 1, 1. The next one is 2. The next one is 3, 5, 8, 13. So far so good. Basically, I'm just adding to, let's go ahead and make sure that it makes sense as to what the next number is. Let me pick another volunteer. Joshua, what's the next number in this sequence?
21.
21. And how did you get it? 8 plus 13. Very nice. Sarah, what's the next number in this sequence? 34. Where'd you get that? Oh yeah, 13 plus 21. Very nice. So you're getting, hopefully everyone's got the pattern here. You're adding the previous 2 numbers to get the next one, et cetera, et cetera. Now the cool thing about this, as with all recursive sequences, this is true of every recursive formula. It is possible to write down an explicit formula for this. Let's see if I can remember it, because I don't have it. It's okay, let's try this. 1 plus radical 5 over 2 to the n. Just a minute, let me write it down. 1 minus radical 5 over 2 to the n. Maybe? I know there's something down there in the denominator. I know the numerator is correct. Let's see if this works. This will, yeah, huh? Yeah. Yeah, that's a golden ratio. Yeah, that's the next thing to chat about here. But let me double check to make sure that this is right. I'll just Google it. This is called Binet's formula, so I didn't come up with this. Binet's formula. I'll just double check. Blah, blah. Come on, just show it to me. Let me do images. Oh, yeah. Oh, amazing. I can't believe I had it memorized. But yeah, that's what it is. That's Binet's formula for the Fibonacci sequence. And you can double check this. If you plug in the number, let's see, what do we have here? 0, 1, 2, 3, 4, 5, 6, 7, 8. If you plug 8 into this, you'll actually get 34, which seems astounding because you've got this radical 5 floating around, but it turns out that all the radical 5s cancel one another and you get a nice integer. So anyway, this is called the explicit formula. And this here is the recursive.
Who made this?
This is called Binet's formula. But it's not all that, I mean, what we're going to be learning over the next week or so is how to go from this to this. So you will be able to come up with Binet's formula yourself. It is not that hard. So you're going to be able to go from that to this pretty easily. It's not all that complicated, but we want to have fun because that's why we're here. So let's play some games. Well, not games. What I want to know is, so I've got some toys, and you can pick your own groups, but you need to be in, there's four groups of toys. So what you're going to do is we're going to start off with the rectangular bricks, the 2x1 rectangular bricks. And what we want to do is we want to tile. So imagine, so start off, and you can draw this on a piece of paper if you need to, but if you don't need to, you can just visualize it or imagine it in your head. It's fine either way. But you can, what we're going to do is we're going to tile 2x-in boards, if you will. So we're going to start with that, and then we're going to do this one, and then we're going to do this one. 1, 2, 3. See the pattern here so far? And I want to know the number of different ways that you can do this. So how many ways can you do this with your little rectangular, I'm calling dominoes, but I dug through my bucket of junk to find whatever I could find. And before I found these, I actually had a bunch of little engine blocks, if you can believe it. So this is like an engine block that I printed up for some game that I thought that we would play in board game design, but I never did. So anyway, so you've got your things, oh, just in case you're not sure what I mean, let's do this. Ready? So here is n equals 1. There's one way to do this. You see it? It's right there. So if you want, you can take one of those and arrange it in this arrangement. Sam needs a friend. Okay, but anyway, there's one. Yeah, Sam's going to become friends with someone in a minute. And then here's, just to make sure that everyone understands, here's the n equals 2 example. There are 2 ways. So to begin my sequence, the first number in the sequence is 1. The second number is 2. Figure out what the third number is. How many ways can you do this board? So this is 1. There's one way. This is 2 ways. How many ways can you do this? How many ways can you do that? Etc., etc. So take a couple of minutes and see if you can work it out. Sarah, if you feel like they're excluding you, you can always work with Peyton. I just want to make sure that you don't feel like you're being left out. Where's that thing? There. Discipleship, distinct. Yipper.
It seems very reminiscent of dihedral groups in modern algebra.
Oh, is this
Well, no, I'm not
dihedral?
familiar enough with the topic. I'm just saying when we did the dihedral group and rotation dihedral,
Uh-huh.
it feels like it's at least linked to it.
Mm-hmm.
I don't know.
Yeah, it's not, no, well, it's not the same. Yeah, sorry, it took a minute to picture what's going on. No, not the same. But yeah, it does feel like you're playing with toys. And you played with toys when didn't she gave you toys? Yeah, okay, paper. I told her I'd 3D print those for her, and she was like, no, I don't need you to. Okay. I would think it would be much more fun if you had a solid. Okay.
Or two.
Or would it be five? Because there's also there's also this.
You could also team up with the shutter down five.
Really not.
There's a tire on the floor. I don't know whose it is. I'll put it over. I don't think we're gonna get to the tires, sadly. Let's save them. I know. I think I gave you 13 or so because I had extras.
Oh, they're all horizontal.
Yeah. Is it like is this and then this and then over? So you wouldn't count that as
That was
So like
beautiful.
if you have
Huh?
one on top
That
of
was
the other,
amazing.
Is that all of them?
That was all of them. That was so amazing. The
Right.
systematic way you did that.
Oh.
I love it.
I just
Did you disagree with it?
I didn't see all of it.
Oh,
But I thought
yeah, it's like magic.
Then
It's like sleight of hand. Do it again. It's so amazing.
Are they all different?
yeah.
Yeah, these
I presume
are
one
these
for every
four discrete down
for operating.
Yeah, they're
are they all identical?
They're identical. They're identical.
So like
So you can swap those to.
one, two, three, four.
I don't know what you're doing. How many you got?
I would get one, two, and three.
Okay, well, the ones here are right. So the four's not. So here, let's do this. Watch this. There's one. There's two. So I don't know if it's cheating. I'm doing what's cheating.
But one is one, two,
And there's three. There's four. That's different.
Times 2 plus 2.
Okay, you want to start again?
There's too many.
Okay, if we were to draw them, there's number one. There you go. I like these guys. Okay, so there's one.
Five
And
is
then you do this.
Yeah, after five I'm done, I can't.
That's
That's
one
too
plus
many.
two.
I think that's too many.
You stand them up like that?
I was just looking like this.
No, that's not. Oh, you're trying to do a three-dimensional
And then I have
cube packing problem or something weird.
For 6 of them?
but then like
I'm kind of thinking. That's like probably the stuff in it.
and you get 13, give it 14, you smell like this. So I'm gonna get 13.
That's so with the next one.
Okay.
Have Sarah do it. She knows how.
14 just sounds wrong. I feel like 14
Got it.
might. Well, it's not.
Oh, okay.
There's one you missed. I saw you doing it. No. I'll show you where it is. It's right here. So you're doing great. No. There's just one. So it's right here. You said, okay, I forget where you were. But then you went like this.
Yeah.
And then you went like this. Which is all good. And then you went like this. And then you went like this. Okay. So there's the one that you missed. Yeah, there's 13. All right, let's do this since now the front group at least has their up through D5 or no D6. You've got through D6. Okay, so D3. Hopefully everyone got 3 for D3. Domino 3. Domino 4 is 5. Did anyone not get 5 for Domino 4? D4.
Wait.
It's if you have 4 of those. There's 5 ways of doing.
Yeah.
Yeah, so I'm using D4 for the number. If you have 4 of those, how many ways can you arrange them? Okay. And then 5, that was 8, wasn't it? And then the front group got 13. They actually went through all 13 of them. You did too?
No. I was just saying.
Mathematically, not.
Mathematically, we didn't actually.
Okay, you didn't verify.
We just assumed we were right.
Yeah, so it's hard. And then if we were to go on to D7, it gets even harder to keep track of all of them. Yeah, it's going to be 21. How do you know it's, what's the guess? What's your guess? Fibonacci. Yeah, this is the Fibonacci sequence. Amazing. Now you might say, well, why is it the Fibonacci sequence? Well, let's talk about what the next number is, D7. Take 7 of those things and put them in a row. I'll do the same thing up here, if I can find a blank space. So here's this is close enough. We'll ignore that. So I've got 7 of these, 1, 2, 3, 4, 5, 6, 7. So far, so good? So here's the deal, is that if you want to think of these 7, there are 2 different ways that this first domino could be arranged. It can either be arranged like this, or it could be arranged like this. 4, 5, there it is. So those are the 2 different ways that the first space could be either vertical or horizontal. Now, if it's vertical, then really what you have here is you have 6 other dominoes that can be arranged any way you want. And the number of ways of arranging those 6 is D sub 6. You can arrange them any way you want. D6 is how many ways they could go. And then down here, I think you probably see what the punchline is. Not much of a punchline is down here. How many ways could I arrange those dominoes? Well, there's D5. And so to get the total for D7, you add together D6 and D5. And we did those 2. Where are they? There they are. D6 and D5. So D7 is 8 plus 13, which is 21. QED. Well, it's not quite a proof, but it's close. I'm sort of showing you where the proof might come from. Let's see. What else we got here? Here, this is what we got. That's a recursive clock. I know. It's just, I searched the internet for images of recursion. And this is one of the images I got. I'll show you the rest next time. A couple of other things about the Fibonacci sequence before we move on, since we're almost done for the day. So Fibonacci sequence. Have I told you about how I do my conversions from miles to kilometers? I haven't? Oh, this is so much fun. So it turns out that the ratio of, if you have miles and kilometers, 5K. You know how many miles 5K is? 3. Yeah, 3. 3. Sorry. 5. I know, it's not exactly. It's close. It's close. And it turns out that the ratio of miles to kilometers is approximately the Fibonacci. It gets better, actually, as you go out. So 8, 13, 21, 34, 55, 89, etc. So just as an example, let's prove this, or not prove. There's no proof. It's just an example. Let me just show you. Where's my mouse? Because it's so cool that this is the case. Now, this is completely coincidental, I should say. This has nothing to, I know a lot of people like to take the Fibonacci sequence and say, look, Fibonacci sequence exists in nature, so therefore God. I don't know about those arguments, but this is definitely not that argument. So you go and find your pine cone that has the Fibonacci sequence in its spirals, and you can wonder at the creation of God, which I do as well. But this is not that, just so you know. This is just a coincidence, but it's a cool coincidence. So I want to do miles to kilometers. Let me see, is there a calculator that shows up? Excellent. And so let's do this. Put a Fibonacci number in here for miles, and like 55, and you're going to get the next number in kilometers. So let's go ahead and hit enter. 89. Round to 89. Let's see. What if I do 89? What's the next Fibonacci number? It's 144. Close enough. It's best in sort of the lower numbers. So actually, I do this if I'm trying to do the conversion in my head. Let's say I want to do 100 kilometers. How many miles is 100 kilometers? I know some of you are like, oh, I know that offhand, but I would break up 100 into like little chunks. So 100 is 55 plus 34, which is 89, I guess. So start with 89. Just a sec. I'll just do this here real quick. So what is 100 kilometers in miles? So 100 is equal to 89 plus 11, which is 8 plus 3. Is that right? I got that? And so then to do the conversion, I just take the previous number, 55 plus 5 plus 2. So that's going to be 62 miles. Let's check it out. What is 100 kilometers in miles? 100 kilometers is 62 miles. Isn't that cool? I don't know. It's totally coincidence, but it mainly works for those Fibonacci numbers that are between like under 100. So there you have it. All right, so what are we doing for next time? I guess we don't have any homework because I'm looking at the homework list here, and it says the next homework is due the 20th. What day is it today? The 18th? Oh, yeah, the 20th. No, not going to happen. Oh, wait, will it happen? I don't even have my book. Just a sec. Let me take a peek. I know, you need to know before you leave. So let me grab my book. Maybe it'll happen. View all recent files. If I can find this in the next minute or two. What page is this? It says, okay, so it says 455. Hold on a minute. This may actually be good. I was thinking that we wouldn't if we didn't get done, but let me try this. 470. We find 455 here. So give me a sec here. Find the recurrence relation with initial condition. 1, 2, 3, 7. 1, 2, 3, 7. Whoops. Ooh, yeah. Everything but 7 is good. I'll adjust the homework, but yeah, 1, 2, and 3 are good. I mean, this is 455. 1, 2, 3. So it says it's online, but I'm going to edit it so that it omits number 7. 7 is fun. we haven't talked about that, and you'll all go berserk if I don't. But and we actually, you're going to look at this and say, wait, we didn't talk about any of this. Well, we sort of did. So do your best. You can read the book. That is an option. I know it's not a very popular option, but you could, look at examples in the book. So there, I've deleted number 7. Everyone can be happy that that's not there. Okay, all set. Hope you have a good day. Thanks for coming. And I'm going to stop the recording in case you want to come argue for points. Remember, you can do it.